Hello, class. This is Mr. Hart. And in this podcast, we want to start our next part of the thermal energy unit, and that is on phase changes. Now, you're probably familiar with phase changes, especially for water, because we can see it go between its different forms, with its solid being ice. When it's liquid water, it's just called water, right? And then when it's a gas, we call it steam. So we've seen these different phases that water can be in, and we can see the phase changes that occur. Okay. And so a phase change is when enough heat energy is given or taken from a substance to change its state, okay, between a solid, a liquid, or a gas. Okay, you can see this pretty easily when you boil water, right? You're adding heat to the water, and once enough heat is in the water, once the temperature gets high enough, then it can start to change phase. It can start to boil and turn into steam, okay? And water is not the only thing that can do this, but it's the most easy to see and recognize. Okay, so we'll just probably stick with talking about water, okay, when we think about phase changes. Okay, but in your other science classes, you've probably talked about phase changes, why it occurs. In physics, we want to start calculating how much heat energy we need, how much heat causes the rise in temperature, how much heat we need to put into something in order to cause it to have a phase change. Okay. Now, in order to do this, we need to actually talk about two different types of heat. Okay. The first type is what we call specific heat. Okay. And the second type is what we call latent heat. Now, specific heat is only for raising the temperature of a substance. So let's say I have a pan of water and it's at 50 degrees Celsius. And I'm trying to get it up to 100 degrees Celsius so I can start to boil it. Okay. I'm going to put heat into that system, but it's only specific heat. Okay, its job is to raise the temperature of that water or that substance. Okay, so it's just going to add heat until it slowly raises the temperature of the water. Okay, that's specific heat. Then once I get up to that 100 degrees Celsius, then I'm going to put in latent heat, and that's purpose is to change the phase from water into steam or liquid into gas, right? And so that heat I'm adding doesn't change the temperature, it only changes the phase. Okay. And so latent heat is a huge part of how things behave, okay? And we don't often think about it because we just assume, once water gets up to 100 degrees, it starts to boil. That's not true, right? If that was the case, if it got to 100 degrees, it would just evaporate instantly and be steam, okay? That's not how it works. You're not boiling your water and then it evaporates all of a sudden and it's, I reached 100 degrees Celsius. No, you have to put in energy. You have to continue to put in heat as it's changing that phase, okay? That's the latent heat. Okay, and how much latent heat you need describes how long it's going to take for that thing to change phase. Okay? All right, so we'll look at latent heat in a second. Let's go back to specific heat. Let's just see how we calculate specific heat. Okay, so the equation for specific heat has a really weird looking equation, but we just need to identify these and it's not as strange. Okay, for specific heat, this big Q just means heat energy. Okay, it's just energy measured in joules, but when we do capital Q, we usually mean heat energy. Okay. Then it's going to take, it depends on a couple of things. It takes into account the mass. It takes into account what we call the specific heat constant. Okay, so the C sub P stands for specific heat constant. Okay. I'll talk about that in just a second. But basically it just describes how much heat you need to raise the temperature. Okay. And then it takes into account the change in temperature or how much you have to change the temperature. So delta T is just change in temperature. Okay. All right. Now that we've identified everything, let's put this into English. Okay. Actually describes what this means. So I have a pan of water and I'm trying to put heat into it and raise its temperature. Well, how much heat energy I need depends on how much water I have or the mass of the water, the properties of the water, which are described in the specific heat constant, and how much I'm trying to change the temperature. So if I'm trying to change it by 30 degrees Celsius and I have 2 kilograms and the specific heat of water or the specific heat constant is 1,000 joules per kilogram or whatever it is, right? I times those all together. That tells me how much heat I have to put into the system. So let's solidify the units. Okay, if we think about this in terms of energy, then heat energy is just joules, right? Okay. Now we know that the mass is going to be in kilograms, and the temperature is going to be either in Kelvin or degrees Celsius. Let's just imagine it's in degrees Celsius for right now. Okay. We're trying to get from kilograms times degrees Celsius to joules. Okay. Well, if that's the case, then this specific heat constant, okay, needs to be joules per kilogram times degrees Celsius. Okay. So it's kind of a weird unit, okay, but if you think about it, kilograms cancel out, degrees Celsius cancel out, and you're left with joules. And this makes sense, right? The specific heat constant is going to tell us how many joules per kilogram and per degree of Celsius or per temperature are needed to make something heat up. Okay. All right, so we described this equation a lot. Let's actually put it into application, and we'll start to see how this all works out. Okay. So let's do this example problem. Okay, so if water has a specific heat of 4,182 joules per kilogram degrees Celsius, how much energy is required to raise 5 kilograms of water by 3 degrees Celsius? Okay, so I have some water. I have 5 kilograms of it. I'm trying to get it 3 degrees hotter. How much energy do I need? Okay, so what we're going to do is we say, okay, well, we know that the specific heat constant is given to us. It's 4,182 joules per kilogram degrees Celsius. Okay. We know that the mass is 5 kilograms. And we know that the change in temperature is 3 degrees Celsius. Okay. Then all we need to do is plug into that equation. Okay, so we're trying to find the heat energy, which we call big Q. That's going to be the mass times the specific heat constant times the change in temperature. So this turns out to be really easy because we just times them all across. So we get 5 kilograms times the specific heat constant, which is 4,182, times 3. Okay, pull out our calculator. So 5 times 4,182 times 3. Okay, and so the specific heat constant, the amount of heat that we need is 62,730 joules. Okay, and there we go. So this is how much energy we need to put into the system to raise it by that much temperature. Okay, and you can see by this problem that water has a very high specific heat. That's why it takes so long for us to boil water. Okay, it took this much energy just to raise that water by 3 degrees. Imagine how long it takes to raise it by 100 degrees, okay? Or how much we need to get it to boil, okay? So it takes a lot of energy, okay? Any type of problem that has water is going to have this specific heat constant, okay? So every type of phase of water, every fluid, every metal, any substance has its own specific heat constant, okay? All right, let's do one more. Just make sure we got this down, okay? So if iron has a specific heat of 449 joules per kilogram degrees Celsius, notice this is a lot smaller because iron heats up a lot faster. How much energy is required to raise 20 kilograms of iron by 50 degrees Celsius? Okay. So again, we just make sure we write down what we know. So the specific heat constant is 449. Make that look like a 9. Joules per kilogram degrees Celsius. Okay, the mass is 20 kilograms. And the temperature or change in temperature is 50 degrees Celsius. Okay, so again, we use the same equation. And again, these work out well. We just times these all across. So we get 20 kilograms times 449 for our specific heat constant times 50 degrees is our change in temperature. Put those all in the calculator again. 20 times 449 times 50, and we get that the amount of heat needed is 449,000 joules. Okay, and if you need to, for certain problems, it's okay to put this in kilojoules if it's easier to express. I would do it for this one. This one's just 449 kilojoules. Okay? Alrighty, but that is how we do the specific heat equation. Okay? Now the latent heat equation is very similar, but it doesn't depend on temperature because you're not actually changing the temperature. Okay? So this is our latent heat equation. Okay, again, Q is our heat energy. Still measured in joules, it's just energy, but we think about it a little bit differently. So we make a big capital Q. So big Q equals mass times the latent heat constant. So basically it's not very hard to do. Basically for each substance that we know of, every material that we know of, there's a certain amount of energy that's required to move it from one phase to another. Okay? So for example, you may have for water a latent heat constant that describes the latent heat needed for changing from liquid to solid or from liquid to gas. Okay? There's a latent heat constant for each one of those. Now, the latent heat constant is just joules per kilogram. The mass is just kilograms. And kilograms divided by kilograms just leaves us with joules for the latent or the heat energy, which is what we want. Okay, so basically we've determined already how much energy we need for each kilogram of a substance to change it from one phase to another. Okay, so these problems are really easy. You just know how much your latent heat constant is, you know how much material you have, and that gives you how much energy you're going to need. Okay, so let's go ahead and try one. All right, so if aluminum has a latent heat of fusion, okay, that's a fancy word, but that means we're changing it from liquid to a solid. Okay, so the latent heat of fusion, okay, is 339 kilojoules per kilogram. Okay, so how much energy is required to melt 8.5 kilogram block of aluminum? Okay, now the heat of fusion can go from solid to liquid or liquid to solid. So in this case, we're going from solid to liquid because we're melting. Okay, that doesn't matter so much with the math. Okay, but then, anyways, we say, okay, our latent heat constant, capital L, is 399 kilojoules per kilogram, and our mass is 8.5 kilograms. So all we gotta do is really simple. We just gotta times these two. So 8.5 times 399. That will give us 8.5 times 399. Okay. 3,391.5. Okay, now be aware of your units. This is in kilojoules. Okay. Now we've got a extra 4 digits here, so we could simplify if you want. We could simplify this down to about 3.4 megajoules if we'd like. Okay. But there we go. So that's how much energy we need to get this aluminum block to melt or the solid block of aluminum to melt if we have 8.5 kilograms of it. Okay. So once we put 3.4 megajoules, that whole block of aluminum will melt into a liquid. All right, let's do one more to make sure we got this down. Okay. So if water has a latent heat of vaporization, okay, that's the fancy word again for liquid to gas or gas to liquid, of 2,260 kilojoules per kilogram, how much energy is required to evaporate 1 kilogram of water? Okay. So what we do is we say, okay, we know that capital L, or our latent heat constant, is 2,260 kilojoules per kilogram. And we know that the mass is 1 kilogram. Okay. This one's really easy because we say, okay, Q equals M times L. Well, 2,260 times 1 is just going to be 2,260 kilojoules. Okay? And again, we could put that as megajoules if we want. But there we go. That's how much heat is needed to evaporate or turn into steam 1 kilogram of water. So just make sure you understand the difference between specific heat and latent heat. Okay? Specific heat only changes the temperature. Latent heat only changes the phase. You can't have both at the same time acting on the same part of the substance. Okay? So just make sure you know which equation you're using and when you need to use them. Okay? And just realize that things don't evaporate instantly or melt instantly. That latent heat does take some time to go through the substance, okay? And you need to supply it before that occurs, okay? But just make sure that you do the homework on specific and latent heat. And let me know if you have any questions, and thank you for watching.